Good afternoon.
Toby had to run to the office to get a book because he left his at home.
Ah,
And he said you needed them today.
I did say that. Weston, did you bring yours today?
Yeah, I always have mine, so.
All right, good man. And how about, is Jada there? It's like her computer is there. Well, well, so, well, Miss Townsend, how was your weekend?
It was pretty good.
Good.
My kids came back from Clarksville, Tennessee, and back home to Arizona, so I'm happy.
Oh, that's good.
Yeah, that's why I was gone those 2 days.
Uh-huh.
But,
Oh, so they were just there for a visit?
yeah, they're moving back down to Phoenix, so
Oh, okay. Well, that is
we'll
much
be
closer.
close to home. Yep.
All right.
Everything going okay for you?
Well, I was sick as a dog over the weekend. And
Uh-oh.
so, you know, when you're so sick that when you're happy to go to work on Monday, that's how sick I was.
I understand that.
Oh man, I was so happy to go to work today. I felt like a caged tiger. I was just ready to go. So
I bet.
so that's
So
good.
are they gonna do their midterm the same days or
Yeah, yeah.
okay.
So on Wednesday and Thursday after
Wednesday and
spring.
Thursday?
Yeah.
Okay.
Yep.
All
So
right,
Jada,
we'll be ready.
you bet. Thank you. Jada, did you bring your book?
No, we had a cultural ceremony this weekend, so I wasn't home all weekend.
Okay. All right.
I guess I tried. My mom was trying to bring it, but she couldn't. Cause like I live in Tuba, so it's kind of
Okay.
hard.
All right. Well, it's going to be really hard for you to. Matter of fact, let's see. I wonder. Um. Huh. I don't think you can do it without your book. Um. Is there a way? Can you get it tomorrow? By class time tomorrow?
Yeah, I'm finally going home today.
All right. All right. Well, okay. Yeah, I can't really teach you how to use the tables in the back of the book if you don't have the back of the book. So I think what I'm going to do is go to the next lesson. So 8.7. So we can do that today instead. So now Tobias has run to the office for nothing. Oh, you. Hey, how you doing?
Good. How are you doing?
I'm okay. So, did you win anything else over the weekend?
We won 2 games at a tournament and lost 2.
Oh, at your softball tournament?
Yeah.
Okay.
And we actually played some basketball against some boys and we won that game. So
Well, of course. I mean,
Yep.
yeah.
we didn't even have shoes on. Still balled them up.
That's funny. I actually, you'll probably lose some respect for me over this, but I actually, in high school, when I was high school age, I would go to the college and play pickup basketball for money. And we, you know, because I wasn't super tall, a lot of people would underestimate me. And so I think my buddy and I, we'd play 2-on-2, and I think our record was probably 48-2, somewhere around there. I mean, we were good. But one of the teams we lost against was a team of all girls. There were 3 girls, but we didn't normally play 3-on-3, and so they wanted us to just draft somebody, and we made the mistake of saying okay. Those girls cleaned our clocks. So anyway, which is kind of funny. But anyway, well, good to see you, Juliet. Yeah, if you make it to the state finals in softball, then I want a T-shirt. Okay, I want a
Okay.
T-shirt that says all the champions or something. So
All right. We'll get you
Anyway.
one if you make it.
All right. Thanks.
That's a good story about the basketball players too, by the way.
Yeah, I thought you would enjoy it. So
Oh yeah.
anyway,
We'll
we'll
let you
see
get
ya.
to it.
See you, Mr. Strong.
All right. Take care. All right. So Tobias, what I really need everybody to have their book, and Jada wasn't able to go home this weekend, and so I'm gonna skip 8-6. So tomorrow, bring your book, okay? And sorry that you had to run to the principal's office. I appreciate you looking out for me, but we're gonna skip 8-6 and go to 8-7, okay? And so hopefully, Jada, you'll be able to have your book. Does the school not have a couple of extra books, Jada?
No, I don't think so. Well, I think Chen still has his.
Okay. Well,
Yeah.
if something happens tomorrow, maybe you can try to track one down, because I know the school had several copies of it, and that
Yeah.
the people that dropped after Calc 1, they should still have their books, or the school ought to have them, one or the other. So, all right. Well, anyway, we won't take time to have you track it down now, but let's just go on to 8-7. Actually, 8-6 and 8-7 both are two of my favorite sections in this chapter. 8-7 is on what's called numerical integration, and the numerical, it's all about the crunching numbers. So this is a lot of calculator work here, but it feels more like 7th grade geometry than Calc 2. All right? So I'll just warn you there. And so most students, because once I teach you the concept, the actual math is much easier on this. And so most students do really well on 8-7. Okay? So the big formula that you have to know here is actually the area of a trapezoid. Okay, and we'll kind of elaborate on that. But if you remember, a trapezoid has exactly one pair of parallel sides, and we're calling those base 1 and base 2. And the formula for the area of a trapezoid is 1/2 the sum of the bases times the height. Okay, now that's kind of how you would see that formula in junior high or in a high school geometry class. Now what we're going to do is tip that trapezoid on its edge, and we're going to say that the height, the distance between the two parallel sides, instead of calling that h, we're going to call it delta x, because we're going to put that along the x-axis. So instead of 1/2 h, it's 1/2 delta x, and then the sum of the bases is y1 plus y2, because those are going to be the y values of the function. Okay, so that's the trapezoid. Now, to really make it calculus, we're going to add up a bunch of these to get trapezoids under the area of the curve, to find the area. So just like way back when we did Riemann sums and we did areas of rectangles, now we're going to do areas of trapezoids under the curve. And see, the thing is you might think about this is that if we made a rectangle and the height was y sub 0, then we would have a huge underestimation here. But if we had y1 be the height of our rectangle, then it would be an overestimation. So this makes it so that our error is much, much less. Okay? Now, if we're going to add up all of these trapezoids, okay, then it's 1/2 times the base. And what we do is we make these base lengths delta x all the same. So that's our interval. Okay? And then the heights, if you look at this first one, its heights are y sub 0 and y sub 1. All right? Then the second trapezoid has for its heights y1 and y2. And then the next one has y2 and y3, and so on and so forth till you get to the very end. Okay? So if you look, that these y values, we're actually using y1 2 times and y2 2 times. And we're actually going to use all of the y values 2 times, except which ones?
The first and the last.
The first and the last. Okay? Excellent. So this is the formula. Now this is what you write down on your guided notes here for 8-7. So the trapezoidal rule says to approximate the integral, the area under the curve, you say t equals, and then the way they write it in the book is delta x divided by 2. I kind of don't like that because usually your delta x is like a fraction. And so then you end up with a complex fraction. So I write it as 1/2 times delta x. And then we have y sub 1 plus 2y sub, y sub 0 plus 2y sub 1 plus 2y sub 2 plus 2y sub 3, all the way till the very end, you just have 1 y sub n. Okay? So here's an example. So let's say we're integrating from 1 to 3, and this is our function. Okay? Now, to get the y values, what you do is you make a table. Use your calculator to make a table. So you put the integrand into your y equals 2x minus 1. Now, you have to be told how many trapezoids to use. And usually it'll say n equals a number. And that's the number of trapezoids. All right? Now, you have to figure out what the width is, the delta x. And the way you do that is you say, okay, so the interval is from 1 to 3. So that's a length of 2. But then you divide that into the number of trapezoids. So you take 2 divided by 4 is 1/2. So that's the same way we did before when we were working with rectangles. So when you do your table, you start with 1, and then you go and you increase x by 0.5 each time, okay? And then you get the y values. All right? Everybody okay on how to get the table? How to make the table? Anybody need me to show that? Okay. So now you set up your formula, and again, it's really geometry. It's not really calculus. So you say 1/2 times, okay, the delta x is the interval divided by n. So 2 divided by 4 is 1/2. And then you have 1 times the first y value, which is 1. 2 times the second y value, which is 2. 2 times the next y value, 3. 2 times the next y value, which is 4. And then 1 times the last y value, which is 5. And so then you can either simplify and then plug it in the calculator, or maybe you don't even need the calculator on some of these. You could just add them up, multiply, and the answer is 6. Okay? All right. I guess I should have asked. Do you all have the guided notes for 8-7? Everybody got that? Yes? Okay. Jada, have you got the guided notes for 8-7? Okay. All right. Well, go ahead and try practice 1A, and I'll leave this example up here. All right, so Weston, when you've got it.
I got 4.
4 is correct. Okay, good job. All right, any questions on that? Okay. Okay, so estimating with the trapezoidal rule. If the graph is concave up, the approximating segments will lie above the curve, and the trapezoidal rule overestimates the answer. If the graph is concave down, the approximating segments lie below the curve, and the trapezoidal rule underestimates the answer. Now, how can you make it so that the error is smaller? What do you think?
More trapezoids.
More trapezoids. Now for us, and we'll talk about this either at the end of class today or first thing tomorrow, when if we don't finish it today. But the trapezoidal rule is actually what your calculator uses when you do that math integral thing. It does the trapezoidal rule, but it uses like 1,000 trapezoids. Why? Because it can. And it can, crank through all of that in no time, because it's just, punching in numbers. And so it can do that. All right, now you might say, well, why do we need to know this if we can just punch it in the calculator? Well, because sometimes we don't have a function. We just have data. In real life, it's really analyzing data. That's where it's all about. So let's look at this one. It says averaging temperatures. An observer measures the outside temperature every hour from noon until midnight, recording temperatures in the following table. So here's the time starting at noon to midnight. What was the average temperature for the 12-hour period? Okay, now, here's the thing. Now, we're actually going back to another idea from Calc 1, and that's average value. Average value was the integral divided by the interval. Now, you only have to divide when you are trying to find the average value, okay? So it's the integral divided by the interval. So we're going to use the trapezoidal rule to find the integral, and then the interval is from noon to midnight, so that's 12 hours. So we're going to find the integral using the trapezoidal rule, and then take our answer and divide by 12. That will give us the average value. Okay? All right. So the average area, the average temperature, the little bar over it means average. So it's 1/2 times 1. Now, why is it 1? Why is the delta x 1 in this example?
Because the time is being changed by 1.
Yes. So the time is taken every hour. Okay? All right. So then we take 1 times the first one, plus 2 times the second one, plus 2 times the third one, all the way to 2 times the last one, or 2 times 58, and then plus the last one. So you don't multiply the first one or the last one by 2. All right, then you put that in your calculator, and you divide by 12, and that gives you your average value. Okay? Now again, if it doesn't ask for the average value, you don't divide by 12. Okay? All right, now, let's see if you can apply that to practice 1B. Okay, so Jada, what would the delta x be in this one?
Would it be 1/2?
It would be 1/2 because we're taking the temperature read, or not temperature, that was the last problem. We're taking the speed readings every half hour. Okay? All right, Tobias, when we use the trapezoid rule to get the average speed, what are we going to divide that answer by in the end?
Is it 9?
No? No, you divide by the, see, like, think about if we were to write this as an integral, what would the limits of integration be? How long is the race going on?
Four and a half hours.
Okay, no, it's 4 hours. See, it
4
actually
hours.
says 4 hours. The reason why you're getting that extra one is because you're getting a reading at the first and at the last. That's why you're getting 9. But it's really only a 4-hour race. Okay? All right. Weston, do you have an answer for us?
Yeah, I got 122.125.
That's it. And it's in miles per hour, the average speed. Okay? So again, it's 1/2 times a half times the first reading is 0, and then 2 times the second, 2 times the third, 2 times the fourth, all the way to the very end, and it's just 1 times that. Okay? All right, any questions on that? Now, I mentioned that the calculator uses the trapezoidal rule. If you ever want to actually set it up, so like say this one, you couldn't, because doesn't have an integral, you would have to know the trapezoidal rule. But if you have your own calculator, if you go to ti.com, you can download a trapezoidal rule program for your calculator, and then you just type in, the number intervals, the y values, and it just spits out the answer. So, it just saves a little bit of work. Okay. Okay, now, there's some stuff about error estimates in this section. We're going to do it a little differently. So we're going to kind of skip that now, and then a little bit if we have time, we'll get to it today. Okay. All right, so then you might ask, well, are there other ways that we could do the area under the curve? We've done rectangles, we did, the midpoint formula, trapezoids. There's another way that you can do it is using paraboloids. So you use parabolas here at the top. And so parabolas can even make it more precise in a lot of functions. Okay? So using the parabolas, the paraboloids, that's what we call Simpson's rule. Okay? So that's the other big rule idea in this. And so to approximate using Simpson's rule, then it's, okay, now you still have your delta x, only instead of dividing by 2, you divide by 3. So the way I write it is 1/3 delta x. Okay, and then the pattern of the coefficients is a little different. So it's 1 times y sub 1, 1 times y sub 0, 4 times y sub 1, 2 times y sub 2, 4 times y sub 3, and then it alternates between 4 and 2 until you get to the very last one. Okay? So just comparing the trapezoidal rule to Simpson's rule. Trapezoid rule has a 1/2, Simpson rule has a 1/3. And then the pattern for trapezoid rule goes 1, 2, 2, 2, 2, and then ends in a 1. Simpson's rule goes 1, 4, 2, 4, 2, 4, and then ends in a 1. Okay? So you need to keep those straight. And because there's certain problems where Simpson's rule is the way to go. So I guess what I'm saying here is on the Calc 2 final, every final I've seen has a trapezoid rule problem and a Simpson's rule problem on it. Okay? And I always like these as a student because I think that it's just number crunching. Okay? But you just have to do a little practice. Okay, so applying Simpson's rule. All right, so here we're going to use Simpson's rule to approximate this integral from 0 to 2, 5x to the 4th dx. So it says n equals 4. So once again, if we go from 0 to 2, and we're going to use 4 of these paraboloids, the width, or delta x, is going to be 0.5. Okay? So that's our delta x. Okay? So now I don't do, again, the way I write it is 1/3 times 1/2. Because I don't like 1/2 divided by 3. I don't like that as a complex fraction. All right, now, the 5x to the 4th, you put into your y equals, and you make your table. So you go in increments of 1/2 or 0.5. Now here they've done it as a fraction. You can do it as fractions or decimals. Okay, so it's 1 times the first y value, 4 times the second, 2 times the third, 4 times the fourth, and then 1 times the fifth again. So you can see, you can just set it up, and then I would just put that in the calculator and let the calculator worry about multiplying fractions and getting common denominators and whatever. Because what this ends up with is 32 and a 12th is our answer with Simpson's rule. Now, once again, the very importance of the trapezoid rule and Simpson's rule is analyzing data. Because often we don't have this 5x to the 4th. Okay? We don't have the function. Now, in a little bit, I'm going to have you compare, like if we wanted to compare the actual value to Simpson's rule. So the actual value, when we have the function, we can calculate by doing the antiderivative. So bring the 5 out front. The antiderivative of x to the 4th is x to the 5th over 5. 5's cancel. So 2 to the 5th is 32 minus 0 is 32. So the exact value is 32. Simpson's rule got us within a 12th. So that would be the error in Simpson's rule. Okay? All right. So in practice 2, I want you to use Simpson's rule for this. See if you can figure out, approximate the integral from 0 to 4 of 3x to the 4th with 4 paraboloids. All right, so Tobias, when you've got the answer.
I got 616.
616 is correct. Great job. All right, anybody not get that? Want me to go over it? Okay. Weston, you good?
Yeah.
Okay, Jada, thumbs up? Awesome. Okay. All right, so we'll talk more about error estimates in a minute. All right, so now basically how we're going to do it is I'm going to have you compare the trapezoidal rule with Simpson's rule. Okay, so for many integrals, Simpson's rule is more accurate than the trapezoidal rule. Okay, I'll tell you in a minute which ones are not. But in general, if you have to choose only one, like let's say you're working for an engineering firm and you need to have an answer, then you usually would use Simpson's rule if you could only pick one. Okay, but we'll see. So I don't know if this makes sense to you, this table here, but N here represents the number of trapezoids or the number of paraboloids. Okay, and so what this is saying is that as you increase the number, then you're going to decrease the error. See, and you can see that here the error, I mean, it's still pretty small, but the error is less with Simpson's rule. And so if your calculator uses 100 trapezoids, see, it's going to be pretty dang accurate. Okay. All right. So what I want you to do is now with this, okay? So compare the trapezoidal rule and Simpson's rule with the actual value of this integral. Okay, so the integral from 1 to 5 of x cubed for n equals 8. So we're going to use 8 subintervals. Okay, now, so I want you to actually give me 3 answers here. So I want you to tell me what the answer is with the trapezoidal rule, Simpson's rule, and then the actual value. So do the antiderivative by hand, not with your calculator, do it by hand. And then that's the actual value. All right, so Jada, when you have the trapezoidal rule answer, let us know.
Okay, give me a minute real quick.
Okay, no problem.
Okay, so I got 20.5.
Okay. I got 157.5. All right, so let's see. Did you get this table right?
Oh yeah, I only went up to 3.
Yeah, so it goes from 1 to 5.
Okay.
Okay. So yeah, you got to include all of them. All right, and then, yeah, that makes sense. All right, let's see. Tobias, tell me your answer for the Simpsons rule when you get that.
I I got 234.
All right. 234. No, it's 156. So let's look at the table. Let's see. Did you do a half times a third in front?
No, I forgot to change it to a third, so that's probably what I missed.
Yeah, so Simpson's rule, yeah, when you were saying your answer, I just realized that would be about right if you did a half times a half. Okay? So the actual answer for the trapezoidal rule was 157.5. For Simpson's rule is 156. All right, so Weston, what's the actual value?
I got 156.
156. So this is the actual value here is 156. So what that means then is that Simpson's rule got us exactly the answer with 8 paraboloids. Whereas the trapezoidal rule was off a little bit. Not a whole lot, but it was off some. Okay? So that's why I say in most cases, Simpson's rule is a little more accurate. All right. Does anyone want me to explain any part of that in a little more detail? Okay. So, so the estimations are sometimes more accurate if we increase the number of intervals. Now, if the function is a polynomial of a degree less than 4, then the trapezoidal rule has no error at all. So if f of x is a polynomial of degree less than 4, then the trapezoidal rule is exactly right. So when given interval lengths from a given area, use Simpson's rule. And I'll explain what that means in just a second here. Okay? So basically here, if you're given a, so here we're trying to figure out how much area this is. Okay? Actually, maybe, well, it says it's 5 feet deep. So maybe we're trying to figure out how much we're trying to drain the swamp or something like that. And so as surveyors, we go and we get incremental lengths across this pond or whatever. And so then what we do is, and so these intervals are every 20 feet. So that's going to be like our delta x. So what we're saying is, in a case like this, when you don't have a function and you're trying to find an area, then go ahead and use Simpson's rule. Okay? So with Simpson's rule, what we would do is we would take, so 1/3 of delta x, which is 20. So 1/3 times 20, and then the first measurement plus 4 times the second one, 2 times the next one, 4 times the next one, 2 times the next one, 4 times the next one, and then plus the last one. And then we just put that in the calculator, and so we get 8,100 square feet. Now, let's suppose that the average depth, it said, was 5 feet. So if we wanted to find the volume of this swamp, then we would take the area times the depth. So 8,100 cubic feet times 5 cubic feet, and that would be 40,500 cubic feet. So it's just multiplying. Now let's say we want to fill this swamp up. We're developing the area here. Okay, we're going to build houses or a mall or whatever. Okay, so we're filling in this swamp and we're going to bring in concrete. So we go to get our concrete, and they sell it by not the cubic foot, but by the cubic yard. Okay, so then how do you convert cubic feet to cubic yards?
Would you divide by 3? Or do something?
Okay, right, because there's 3 feet in a yard, but how many cubic feet would be in a cubic yard then?
$27?
27. 3 by 3 by 3. So we would take this answer and divide by 27, and that would give us our volume in cubic yards. Okay? Now, I tell you that because on the last practice problem here, okay, it says the town wants to drain the swamp, okay, but it wants the answer in cubic yards. So you're going to have to do this, all right? So what I want you to do, because we're going to run out of time here before we can go over the answer. So I want you to go ahead and do that problem before class tomorrow, and we'll go over it first thing. So you're going to need Simpson's rule, and then you divide, then multiply by the depth, and then divide by 27, and you'll get your final answer. So we'll go over that, and then so bring your book tomorrow, Jada, if you can, everybody, okay? And we'll go from there. So thanks, you guys. We'll see you tomorrow.